Good morning, calculus friends. Welcome to section 4.4, Indeterminate Forms and L'Hopital's rule. Examples of indeterminate forms. We've talked about this, the difference between undefined and indeterminate. Indeterminate forms, we've used things like 0 over 0. Remember when we were doing limits and we got something of the form 0 over 0. We concluded that we don't know the value of this. It depends on where the problem stems. Same with infinity over infinity. Infinity over infinity may be 0, maybe 7. Depends on the problem from which it stems. 0 times infinity, positive or negative infinity. We don't know the value of this either. That's another indeterminate form. Infinity minus infinity is also an indeterminate form. 0 to the 0 power and 1 to the infinity power. None of these we have a concrete value for. Depends on from which the problem stems, and we have to investigate further. So let's do that. Let's remember from our very first conversation on limits, we found the limit as x went to 0 to be 1. We did this using a table of values. And the graph of this to make this conclusion. Okay, graphs aren't always clear, and table of values don't always give us exact numbers. So we're looking for a more calculus approach to finding these limits. So that's the title of today's section, L'Hopital's rule. Right, L'Hopital's rule says, suppose we have one of the following cases. 0, the limit as x approaches a can be a constant or infinity. And we have a quotient, some function f of x over another function g of x. And when we take this limit, we get 0 on top, or 0 and 0 on the bottom, or we get infinity on top and infinity on the bottom. One can be negative, they both can be negative, or they both can be positive. So a can be any real number. We can take the limit as x approaches any real number or positive or negative infinity. If f and g are both differentiable, we have this really, really cool rule. L'Hopital came up with it for us. It says the limit as x approaches a. This only works if we have 0 over 0 or infinity over infinity is equal to the limit as x approaches a of the derivative of the top function over the derivative of the bottom function. Now be careful, this is not the quotient rule. Even though we are starting with a quotient, L'Hopital's rule does not apply the quotient rule to this function. It just says you can simply take the derivative of the top and the derivative of the bottom. This is the only time in calculus where we're allowed to just take the derivative of the top and the derivative of the bottom when it involves a limit and we have an indeterminate form, 0 over 0 or infinity over infinity. So take a minute, pause, write this down. We'll move on to our example. So let's revisit the limit as x goes to 0 of sine of x over x. If we do direct substitution, or we just look at the limit of the top compared to the limit of the bottom, well, as x goes to 0, the sine of 0 goes to 0, and as x goes to 0, 0 goes to 0. So L'Hopital's rule says, well, if you have an indeterminate form, 0 over 0, we can rewrite this as x goes to 0 of the derivative of the top, the derivative of the sine is the cosine, and the derivative of the bottom is 1. So we use L'Hopital's rule here. LH is my abbreviation for L'Hopital. And now when we take the limit of the top and the limit of the bottom, the limit laws say if we have a quotient, the limit of the quotient is equal to the limit of the top of the limit over the bottom. We get the top is going to 1. We do direct substitution, and the limit as x goes to 0, 1 is 1. So we get 1 over 1, which is 1, which is the same result we got when we used the table of values and the graph. All right, so let's check out another example. Previously, we used that little trick when we had degree of the top. We have a rational expression. We have the degree of the top is equal to the degree of the bottom. We concluded using our little trick because the degrees are the same. The limit as x goes to infinity. Now this only works for infinite as x goes to infinity, limits at infinity. It's the ratio of the leading coefficients. But let's apply L'Hopital's rule to see that it works here too. So as x goes to infinity, infinity squared times 2, minus 4 is irrelevant. My numerator is going to infinity. As x goes to infinity, this bottom expression, which is also a quadratic, also goes to infinity. So we're allowed to use L'Hopital's rule here because we have infinity over infinity. And L'Hopital's rule says that this is equivalent to the limit as x goes to infinity of, take the derivative of the top, 4x minus 0 over the derivative of the bottom, 6x plus 2. All right, so it doesn't look like we made much progress, but this is a new function whose limit is equivalent to the previous one. As x goes to infinity, we see that the numerator goes to infinity and the denominator goes to infinity. So we're still in this position where we have an indeterminate form, so we can apply L'Hopital's rule again. We can keep doing this until we get a result. So as x goes to infinity, because we have infinity over infinity, we can take the derivative of the top over the derivative of the bottom. And as x goes to infinity, 4/6 doesn't change. 4/6, we simplify this down to 2/3. So I know it was easier just to use the idea of the ratio of the leading coefficients, but just showing you the process of L'Hopital's rule and showing you that we might have to use it more than once. We use L'Hopital's rule twice here, and we get the same result. So the limit as x goes to infinity of 2x squared minus 4 over 3x squared plus 2x minus 1 is still 2/3. Remember, we want to try to avoid using a table of values. Table of values here would not necessarily, you may not recognize this nice number 2/3 because it would give us an infinite decimal. All right, so let's keep going because the more problems we do, the better we get at it. All right, as x goes to 0 of 2 to the x minus 3 to the x all over x squared minus 2 to the x. Well, 2 to the 0 is 1 and 3 to the 0 is 1. So this gives my numerator, when I do direct substitution, 0. And it gives my denominator 0 because 0 squared minus 2 times 0 is 0. So this is a perfect candidate for L'Hopital's rule. So L'Hopital says if we have something of the form 0 over 0 or infinity over infinity, we can take the limit of this function is equal to the limit of the derivative of the top. The derivative of 2 to the x is 2 to the x natural log of 2. Now remember, this is an exponential function, not a power function, so we may not apply the power rule. The derivative of a constant to the variable x power is the same function times the natural log of the base, minus 3 to the x natural log of 3, all over the derivative of the bottom, 2x minus 2. All right, so now we're going to plug in. All right, well, when we plug in 0, we get 2 to the 0, which is 1, times the natural log of 2, 3 to the 0, which is 1, times the natural log of 3, all over negative 2. So now this turns out to be a nice number. It's the natural log of 2 minus the natural log of 3, all over negative 2. Because, if you didn't quite see that, right, this is just going to 1. And 3 to the 0 is also 1, and this goes to 0. So we get 1 times the natural log of 2 minus 1 times the natural log of 3 all over 0 minus 2. And this is the final answer. You may see this in your book written as the natural log of 3 minus the natural log of 2 all over positive 2. There's just a lot of negatives going on here, so if we multiply the top and the bottom by negative 1, you don't have to do this, but just recognize that this is what they might do in the book. It just gives us a more visually pleasing answer. So, final answer, natural log of 3, minus the natural log of 2. You know what, I'm going to take this up one step. I'm going to pull this 2 out front. Dividing by 2 is the same as multiplying by a half, right? Just to keep you aware of different forms of the answer. But we also have a property of logs. If we have the difference of logs, we can combine this and make it a quotient. Natural log of 3/2. Natural log of a minus the natural log of b is the natural log of a divided by b. So this is perfectly acceptable for an answer. Not quite sure how XYZ would expect you to plug it in, but just keep in mind these are alternate ways to express the same answer. All right, so not too terrible. All right, let's revisit another problem. A common example in log problems. The limit as x goes to 6 of 1 over x minus 1/6 over x minus 6. If we plug in 6 here and here, you see that we get 0 over 0. So this is a great problem to apply L'Hopital's rule. Right, if we apply L'Hopital's rule says we can take the limit of the derivative of the top. The derivative of the top is, well, remember 1 over x is x to the negative 1 power. So we take the derivative, it's going to be negative 1, x to the negative 2. The derivative of 1/6 is 0, so minus 0, and it's going to be 1 minus 0. All right, so this may be a little tricky to see, so I'm going to clean this up a little bit. That's just 1 in the denominator, so this numerator becomes negative 1 over x squared, and this is just 1. So this is going to be the limit as x goes to 6 of negative 1 over x squared. When we clean that up, now as x goes to 6, we now can do direct substitution, and we get negative 1 over 36. So we did this last time back in chapter 2 when we did limits, and we multiplied the top and the bottom by the common baby denominator. So we would have multiplied the top and the bottom by 6x, and we would have done algebra, and this is the result we would have gotten that way too. So either way is fine, but L'Hopital's rule provides us with a really great tool to sort of avoid a lot of that confusion. All right, so a couple more. As x goes to 3 of x minus 3 over x squared minus 9, you might notice that the denominator is a difference of squares. We could just factor this, x minus 3, x plus 3, cancel out the common factors and do direct substitution. Or, because when we plug in 3, we get 0 over 0, we can use L'Hopital's rule, and we get that this is equivalent to the limit as x goes to 3 of 1 minus 0 all over 2x minus 0. Now we can do direct substitution, plug in 3, and we get 1/6. Right, so a little bit easier than the algebra. All right, let's check out this guy. The limit as x goes to infinity, 2 minus the natural log of x over x squared plus 4. Well, as x goes to infinity, you have to know how the natural log behaves. Remember, the graph of it looks like this. And it does shoot off slowly to infinity. So this is y is the natural log of x. It shoots off slowly to infinity, but it does go to infinity. And then this x infinity squared plus 4, you get bit numbers bigger and bigger and you square them. The denominator is definitely going to infinity. But here we have 2 minus bigger and bigger numbers, so that's going to negative infinity. So infinity over infinity, either one can be positive or negative. They both can be positive, they both can be negative, or one of each is still an indeterminate form. So this says take the derivative. L'Hopital's rule says we can take the derivative of the top and the derivative of the bottom. So the limit as x goes to infinity is the derivative of the top, which is 0, minus the derivative of the natural log is 1 over x. And the derivative of the bottom is 2x. All right, so here we want to clean this up a little bit. Do the algebra, put it into a form that makes more sense. So I'm going to multiply the top and the bottom by x to get rid of the fractions and the fractions. And we're going to get the limit as x goes to infinity, and it's going to be negative 1 over 2x squared. Now, as x goes to infinity, we have a constant over infinity. And if you remember from our sections on limits, as a denominator gets bigger and bigger, the whole fraction gets closer and closer to 0. So we can use our previous methods and conclude that this limit is going to be 0. All right, so that is examples of 0 over 0, infinity over infinity. Take the derivative of the top, the derivative of the bottom. So again, keep in mind what L'Hopital's rule says. We have to have something of the form 0 over 0, or infinity over infinity. One can be positive, they both can be positive. One can be negative, they both can be negative. Only in these cases are we allowed to use this quotient and take the derivative of the top and the bottom. That being said, how do we handle these types of indeterminate forms? Right, here we have an example. The limit is x goes to infinity of x times e to the negative x. Well, as x goes to infinity, e to the negative x, that's 1 over e to the x. This is going to go closer and closer to 0. So we actually have infinity times 0 here. And infinity times 0 is an indeterminate form. We can't make the conclusion that this is infinity or 0. We have to do something calculus-based to determine this value. This could be 7, it could be infinity, it could be negative 10. All right, so infinity times 0. Well, if we just think about what e to the negative x means, what I had just said, this is the same thing as x times 1 over e to the x. Agree? So x times e to the negative x is equivalent to, so this is just algebra, right? Which is equivalent to, I'm just going to write it as a quotient, x over e to the x. So that's still just algebra. Now when I write it this way, I get infinity, and e to the x, as x gets really big, also goes to infinity. So now it's of the form infinity over infinity, and I'm allowed to use L'Hopital's rule. So now I can apply L'Hopital's rule because it's in the proper form. I can take the derivative of the top, which is 1, and the derivative of e to the x is just e to the x. Whoops, don't change the problem as x goes to infinity. So as x goes to infinity, 1 stays 1, e to the x goes to infinity, and a constant over very large numbers approaches 0. Right, so this was obvious because e to the negative x, we can just throw that in the denominator and create a quotient of the form necessary to use L'Hopital's rule. But let me just give you a little side note algebra-wise here. If you have a product that you want to turn into a quotient, you can always turn a product into the quotient by picking one of the two factors and putting it in the numerator and then putting the reciprocal in the denominator. So f times g is equivalent to f divided by 1 over g. Or we could write this as the other function in the numerator and the reciprocal in the denominator. So these are all algebraically equivalent, and that's going to help us in a minute to do the remaining problems. So this is going to be an important algebraic trick that will be helpful for us. All right, so remember, you can only use L'Hopital's rule if you have something of the form 0 over 0 or infinity over infinity. If we have the indeterminate product infinity times 0 or 0 times infinity, we turn it into a quotient, then we can use L'Hopital's rule. The limit is x goes to infinity of x times the natural log of 1 plus 3 over x. All right, so let's think about this a little bit. This is a product. As x goes to infinity, this goes to infinity. As x goes to infinity, this whole piece goes to 0. So then what we end up getting is the natural log of 1. So this whole piece, well, the natural log of 1 is 0. So we have something of the form infinity times 0 again. Now remember, this is an indeterminate form, but we can't apply L'Hopital's rule until we turn this into a quotient. So here's where we want to use this cool little trick right here. Right, and turn this product into a quotient. So using algebra, we're going to turn this into a quotient. So we can do the limit, and we pick one to leave on the top and the other to put the reciprocal in the denominator. So I can either leave the x on top and do 1 over the natural log of 1 plus 3 over x, or I can leave the second function, the natural log of 1 plus 3 over x, and put 1 over the other function in the denominator. Now, either one of these are going to they're going to produce the same result. We just have to decide which one we want to work with. If we look here, we now are going to have, let's see, I want a different color. If x goes to infinity, we're going to have infinity. And then now remember, this goes to 0, and 1 over 0 will make this whole denominator go to infinity. Right, so we have something of the form infinity over infinity. If we put it into this form, then as x goes to 0, as x goes to infinity, this goes to 0. So we'll have the natural log of 1. So the numerator will go to 0. 1 over bigger and bigger numbers. So either one will produce a result which we can use. We get infinity over infinity for this form, 0 over 0 for this form. So we have to decide, the next step will be to take the derivative of the numerator and the derivative of the denominator. Here the derivative of the numerator is really nice, it's just 1, but the derivative of the denominator here is going to be quite hairy. Not impossible, but not very nice. Whereas if I look at this example over here, I'd much rather take just the derivative of the natural log of 1 plus 3 over x as opposed to 1 over the natural log of 1 plus 3 over x. And then this is not super nice. It's not as nice as this, but it's a lot better than that one. So I'm going to go with this one. So I'm going to use this guy right here, and this is the problem I'm going to continue with. The limit as x goes to infinity because I believe taking the derivatives will be easier. The natural log of 1 plus 3 over x all over, I'm going to turn 1 over x into x to the negative 1 power. So now I can use L'Hopital's rule because I have 0 over 0. And this is going to be equivalent to the limit as x goes to infinity of the derivative of the top. And the derivative of the top is 1, the derivative of the natural log of anything is 1 over what's inside times the derivative of what's inside. Well, the derivative of 1 plus 3 over x is 0 plus, well, this is 1 plus 3 over x is equivalent to 1 plus 3x to the negative 1. So I'm going to use the power rule, bring the negative out front, negative 3x to the negative 2. And then the derivative of x to the negative 1 is negative 1x to the negative 2. All right, so this, you might look at this and say, oh, goodness. But it's really not that bad. I'm just going to clean it up a little bit. This is 1 over 1 plus 3 over x times negative 3x to the negative 2, all over negative 1x to the negative 2. And if you notice, these guys cancel out, and so does that negative. So this really isn't all that horrible. So let's clean it up a little bit. This is just going to be the limit as x goes to infinity of, well, that's just a 1 in the denominator, so it's 1. Oh, times 3. I'm going to make that a 3 because we have 1. Don't lose that 3. 1 plus 3 over x. And as x goes to infinity, the only term that gets affected is this piece right here, and 3 over larger and larger numbers goes to 0. So this is just going to be 3 over 1 plus 0 is equal to 3. So now remember, we started off with something of the form infinity times 0. Right here, we had infinity times 0. As x gets closer and closer to infinity, this product gets closer and closer to 3. So you can test this by putting larger and larger numbers into this and seeing the result your calculator produces. But would like to be able to have you find these limits using calculus as opposed to just popping things into your calculator. So here, the indeterminate form, infinity times 0 equals 3. Woohoo! All right, let's try another one. Because these are fun. What do I have next? All right, let's do this guy. All right, as x goes to 1 from the positive side, well, if we put numbers closer and closer to 1, this gets closer and closer to 0. Right now here, you have to be a little bit comfortable with your trig functions. The tangent of pi over 2 times x, well, the tangent is undefined at pi over 2, so as x gets closer and closer to 1, this produces outputs closer and closer to the tangent of pi over 2, which is undefined, but again, think of the graph at pi over 2, the tangent looks like this, and it shoots off to infinity. So this is infinity. So we have something of the form 0 times infinity. Now this is an indeterminate form, but we can't apply L'Hopital's rule in this form. We have to change it to a quotient. So we're going to use algebra. Limit as x goes to 1 from the positive side. We can either do x minus 1 over 1 over the tangent of pi over 2 times x. Right? Or we can do the limit as x goes to 1 from the positive side of the tangent of pi over 2x, 1 over, let's do, yeah, x minus 1. Here we go. So either one will work, but if you're, I'm going to go with this guy because I see this as the limit as x goes to 1 from the positive side of x minus 1. Now remember, 1 over the tangent is the cotangent, so we can actually turn this quotient in the denominator to just a trig function, right? All right, so I'm going to go with this guy. We could do this one too, but I can eliminate one of the fractions in this form, where here I can't eliminate one of the fractions, and we're going to create another fraction inside of a fraction. So I'm going to go with this guy. So now as x goes to 1, we're going to get 0. And the cotangent of pi over 2 is the cosine over the sine. And as x approaches 1, and we take the cosine of pi over 2 over the sine of pi over 2, that's going to get closer and closer to 0. So the cotangent of pi over 2 is defined, and it's 0. So by direct substitution, we see 0 over 0. We can use L'Hopital's rule. And L'Hopital's rule says we take the derivative of the top, which is 1, and then the derivative of the bottom, which is the derivative of the cotangent, and the derivative of the cotangent would be the cosecant of pi over 2x times the cotangent of pi over 2x, right? Times the derivative of what's inside, pi over 2. All right, again, now this is just dependent on how comfortable you are with your trig functions. As x goes to 1, the numerator is going to stay at 1. The cosecant of pi over 2 is 1 over the sine of pi over 2, and 1 over the sine of pi over 2 is 1 over 1, so this is just 1. The cotangent of pi over 2 is, would be the cosine over the sine, and the cosine of pi over 2 is 0. Oh, this is not coming out right. Where did I do? All right, hold on. Let's see. I'm going to rewrite this because something's not. I'm not sure if I made a mistake there. Bear with me. I'm definitely not redoing this whole video for this one problem. Let's see. 1 over the cosecant is 1 over the sine of pi over 2, right? And then this would be cosine of pi over 2x all over the sine of pi over 2x times pi over 2. Right? And that's going to be sine squared. Oh, wait, I'm not sure. All right, what did I do? What's the derivative? Oh, I know what I did. Because the derivative of cotangent is not cosecant cotangent. Ah, don't make this mistake. I knew that wasn't coming out right. I apologize, but I am allowed to make mistakes. So let's go revisit. The derivative of the cotangent is not the cosecant cotangent. The derivative of the cotangent is the cosecant squared. So you have to take derivatives correctly in order for this to work. L'Hopital's rule, the derivative of the top. I apologize. Derivative of the top is 1. The derivative of the cotangent is the cosecant squared of pi over 2x times the derivative of what's inside. All right, now the cosecant of pi over 2 is equal to 1 over the sine of pi over 2, which is equal to 1. So as x gets closer and closer to 1, this stays 1. This all goes to 1. There we go. And then this is going to be 1 over pi over 2, which is equal to 2 over pi. 1 divided by a fraction is the same as 1 times the reciprocal. There we go. I apologize for that. That's it. So here, 0 times infinity comes out to be 2 divided by pi. All right, I've got 3 more. I have 4 more examples here. So these videos take forever to download. All right, so stay tuned for infinity minus infinity. 0 to the 0 power and 1 to the infinity power. That will be 4.4 part 2.